Okay, in this this video we're going to talk about escape velocity. Well, what is escape velocity? Well, if we have a massive object and we want to launch a projectile away from this object with a certain escape velocity, such that it won't, if you like, feel the gravitational potential due to this object, then the speed with which you've given the object to do that is called the escape velocity. And what you have to remember is we're going to use two principles here. We're going to use energy conservation which tells me that the energy before is equal to the energy after. So before, if you like, the projectile is sitting here on the edge of the planet, and the planet has a certain radius, big R, and this projectile has a mass of little m. And what's the after scenario? Well, afterwards, in effect, we've got to a distance of infinity where the potential and gravitational potential energy due to this mass is zero. And if you remember from the previous video, that at this distance here, then the object just about stops and doesn't turn around and fall back down to Earth again. So what is this? Well, let's just make some space. What's the total energy of the system before? Well, we have a gravitational potential energy, which is minus big G m little m over r. That's the gravitational potential energy at this point, bringing this mass little m from infinity to a point r from the center of mass of big M. And then it also has a velocity, so it therefore has a kinetic energy, and if it's got an escape velocity v ESC, then the kinetic energy of this projectile will be half mv ESC squared. What about the total energy after, when it's at infinity? Well, it just stops, therefore its kinetic energy is zero. And by definition, at infinity, the gravitational potential energy is also zero. So we have that the total energy before is this, and the total energy after is zero. So we can simply just equate total energy before equals total energy after if we assume no other losses. But obviously in real life you lose energy due to air resistance if the planet has an atmosphere. So, but let's assume we don't have an atmosphere, so we just put minus big G m little m over r equals plus a half mv escape squared equals zero. Move this thing over to the right hand side, I get a half mv escape squared equals big G m little m over r. What cancels? Well, the little m, so the mass of the projectile is not relevant, interestingly enough. And I'm to divide both sides by a half, so I get 2 gm over r, and then obviously I have to square root it. Let's do a worked example then. Put in some values for Earth. Bring up my calculator. So what's the value of the escape velocity for Earth? The value of big G is 6.67 times 10 to the minus 11 times the mass of the Earth, which is 5.97 times 10 to the 24 divided by the radius of the Earth, which is 6. 38 times 10 to the 6 meters, and I get an answer of 11.2 times 10 to the 3 meters per second squared.